In this video, we solve problem 13.3.079 from Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find 4 second partial derivatives and observe that the mixed partials, the second mixed partials, are equal. So we've got z, and z is a function of 2 variables. And if we want second partial derivatives, the first thing we need to do is compute first partial derivatives. So we'll compute the partial derivative of z with respect to x, that's Leibniz notation, or if you prefer, you can use subscript notation. Now that's the same thing as taking the partial with respect to x of z, and z is x to the 4th minus 5xy plus 8y cubed. So you're just going to start by taking these first partial derivatives. Now remember, whenever you're taking a first partial derivative, actually any partial derivative, you're treating this variable as if it varies, and you're treating all the other variables as if they're constants. So when I take the partial derivative of x to the 4th, since I'm taking the partial derivative with respect to x, it's pretty much the same as taking the partial, or the regular derivative, or the ordinary derivative of x to the 4th with respect to x. So we bring the power down, multiply by x to the 1 less power. Now over here, we want to be careful. We're treating y as a constant. So I've got this -5 and this y here, and I want to think of both of those as constants. So I'm taking the partial derivative with respect to x of this expression, but I want to think of it as a constant times x. The derivative of a constant times x is just the constant, and the constant in this case is -5y. And then over here, I've got a constant, but no function of x. If we're treating y as a constant, y might as well be 3. This might as well be an 8 times 3 cubed. It's just a number. So when I'm taking the partial derivative with respect to x of this, I'm thinking of that as just 8 times a number cubed. And the derivative of that constant with respect to x is just 0. So we get 4x cubed minus 5y as the partial derivative of z with respect to x. And I'm just writing down what we just talked about. So we're treating y as a constant and differentiating with respect to x. Okay, now in order to find second partials, we also need to find the second, or the first partial derivative of z with respect to y. So we're going to do the same thing, we're just going to do it the other way around. We're computing the partial of z with respect to y by treating the other variables as constants, in this case x. So we treat x as a constant, and we differentiate with respect to y this time. Now you've got some options. You can use Leibniz notation, that's the partial of z with respect to y, or you can use subscript notation, that means exactly the same thing. Now both of those are equal to this. Now this is an operator. This says take the partial with respect to y of whatever is in these brackets to the right. Inside the brackets, I write my function. And now I'm just differentiating with respect to y and treating x as a constant. Since there are no y's in this, that's just a constant. The derivative of a constant with respect to y is 0. Over here, I've got a -5xy. I want to think of that as a constant times y. The derivative of a constant times y is just the constant. And then this last one, there are no x's in it. So the derivative of 8y cubed with respect to y is the same as it was in Calc 1. You bring the 8 down, you multiply by the derivative of y cubed, which is 3 times y squared. You're bringing that power down and multiplying by y, the 1 less power. And of course, we can simplify this. And so we've got that. Now we were asked for the second partial derivatives. So we're just going to compute derivatives again. Now since z is a function of 2 variables, so if you wanted to, you could call this f of xy or z of xy. When I take the second partial derivatives, because I had 2 variables, I'm actually going to have 4 second partial derivatives. So let's first compute the second partial of z with respect to x. You can use that subscript notation, but I believe Leibniz notation is what is shown in your homework. Remember how this works. You're taking the partial with respect to x of the first partial of z with respect to x. So you've already done this part. The first partial of z with respect to x is right here. So all you're doing is you're taking, oops, sorry, that's off the screen. You're taking the derivative of this with respect to x. So that goes right here. So I've got the derivative with respect to x of that first partial of z with respect to x, which is 4x cubed minus 5y. The derivative of 4x cubed with respect to x just comes from using the power rule. So you've got 4, then you bring the power down, multiply by x to the 1 less power. And then the derivative of negative 5y, well, if y is a constant, and we are taking a partial derivative, so you're treating y as a constant, the derivative of that constant with respect to x is 0. So we just get 12x squared, and that is the first answer that WebAssign wants. Now we want to compute the mixed partials as well. So we're going to compute the partial of z with respect to x, and then with respect to y, and the other way around. Now Leibniz notation and subscript notation look a little different in this case. Notice I've got an x first and then a y. That tells me I take the partial derivative with respect to x, and then I take its partial derivative with respect to y. Now this is in the reverse order, but I think it makes sense if you think of it in terms of operators. This is saying take the partial with respect to y of the partial of z with respect to x. And it's the same partial of z with respect to x that we computed earlier. So you're just taking the partial of 4x cubed minus 5y. That's the partial of z with respect to x, and now because we're finding this mixed partial, we're taking the derivative of that with respect to y. Derivative of 4x cubed with respect to y is 0 because there are no y's in that. It's just constant with respect to y, so I get a 0. And then this is a constant times y. The derivative of a constant times y is just our constant. So we get negative 5 as our answer. That's the partial of z with respect to x and then y. And remember, you read this one right to left. You take the partial of z with respect to x and then y. Now our mixed partials should be equal. This time I want to take the partial derivative of z with respect to y and take its derivative with respect to x. In subscript notation, we would represent that this way. So I'm taking the partial with respect to x of the partial of z with respect to y. That's what goes right here. Actually, I think I'll write that down. Way too much space for that, but you get the idea. And then I'll go up here and look for my partial of z with respect to y. That was negative 5x plus 24y squared. So that is what I'm taking the derivative of right here at the bottom. That's my partial of z with respect to y. So for this mixed partial, I take the partial of z with respect to y, and I take its partial derivative with respect to x. The derivative of negative 5x with respect to x, just a constant times x, just the constant. And there are no x's in this 24y squared term, so that might as well be a constant. The derivative of a constant with respect to x is 0. And so we get negative 5, and that's a very good sign. That means our mixed partials did turn out to be equal, and we were expecting that. And we even said, observe that the second mixed partials are equal. So now we're observing, we say, yep, that's right. And we did the second partial of z with respect to x. Then we did the two mixed partials. Now we want to take the second partial of z with respect to y. So you're just taking the partial of z with respect to y, and you're taking its partial again with respect to y. So it's just a little bit of repetition. The partial of z with respect to y was negative 5x plus 24y squared. And we're taking the derivative of that with respect to y now. The derivative of this constant with respect to y is 0. The derivative of this function with respect to y is just that 24, and then we use the power rule for y squared. You bring the constant down and multiply by y to the one less power, and so you get 48y. And that's it. Those are our 4 second partial derivatives. So I've got my second partial with respect to y, the 2 mixed partials, and then the partial with respect to x.